Phase transitions, processes that we see every day, such as the boiling of water or the condensation of vapor on the side of your glass. Now, how do phase transitions start? If we zoom in microscopically at gas molecules as it starts to condense, what would we see? The first steps of condensation or any other phase transition refers to the process called nucleation. In condensation, nucleation occurs as gas molecules cluster together to form a nucleus. A nucleus can experience either growth by clustering with more molecules or decay by losing molecules. At a certain size, the nucleus will only continue to grow until it becomes a droplet visible to our eyes. In binary nucleation, it is crucial to study the ordering in the nucleus. This is possible with molecular dynamics. This method works by applying Newton's laws of motion and established potential models to generate a trajectory that simulates the movement of atoms. Now, why the interest in water, n-Nonane, 1-butanol, and ammonia? Recent studies showed that atmospheric aerosols, which are human health hazards and agents of climate change, are frequently comprised of volatile or semi-volatile molecules. In this work, the structural features of the nuclei, from homogeneous vapor-liquid nucleation of the six binary combinations from water, n-Nonane, 1-butanol, and ammonia, is investigated using molecular dynamics. In the MD simulation, each system was equilibrated at 700 Kelvin and quenched to 230 Kelvin to initiate nucleation. An additional 5 and 15 nanoseconds of production run were completed for ammonia-containing and non-ammonia mixtures respectively. In the radial density profile of water and butanol clusters, both nucleating species is observed across the entirety of the clusters. This signifies the absence of phase separation between water and butanol, despite having a macroscopic miscibility gap. Another observation is the butanol enrichment at the cluster surface, while water concentration is higher at the interior. Cluster snapshots verify that the surface is dominated by butanol. These results are also similar to that of the butanol ammonia system. Reports on water nonane show a lack of mixing, which verifies the microscopic immiscibility between the involved species. The involvement of both molecule types in the generated clusters, along with the absence of mixing, implies the occurrence of adsorption. These results agree with the earlier literature, where a pronounced miscibility gap was observed between water and nonane. The results also support assumptions of earlier literature that adsorption, leading to a mimicking of heterogeneous nucleation, takes place between immiscible nucleating vapors. Microscopic immiscibility and adsorption is also observed in nonane ammonia. In water ammonia, both nucleating species is present throughout the entire cluster, but the concentration of ammonia is enriched at the surface, while more molecules of water are noticeable toward the interior. The nucleation enhancement of binary mixtures of water and ammonia, which was established in earlier literature, is likely caused by this mechanism. Given that ammonia has less surface tension, its position at the cluster surface decreases surface energy. The results for nonane butanol indicate homogeneous mixing between the two nucleating species. Additionally, this further verifies that the reluctant co-nucleation reported for n-Nonane and alcohol mixtures is minimized in nonane butanol by the relatively low alkyl tail of 1-butanol. This study revealed diverse ordering features of the six binary combinations from water, n-Nonane, 1-butanol, and ammonia. It was also possible to relate the observed behavior to the molecular properties of the contained nucleating species. Furthermore, with the investigated molecules being among the predominant species that constitute atmospheric aerosols, this study has contributed to the further understanding of particulate matter in the air.